All right, guys, this is a really important section right here. We're going to start talking about what are called normal distributions, otherwise known as the bell curve. And so a bell curve is a symmetrical distribution. We'll get deeper and deeper into it as we go. I just wanted to share with you before we get into it the most hilarious cartoon that was sent to me by my good engineer friend Kip. So this was around Halloween. Kip sent me this cartoon. I don't know how well you can see it. It might be an advantage not to be able to see it. But we have a picture of a normal distribution as I've drawn on the board. And then here's a picture of a paranormal distribution. Isn't that awesome? Thank you, Kip, for that. What do you guys think about that? All right, well, anyway, never mind. So let's talk about some general things about the normal distribution, the bell curve. First of all, it needs to be mentioned that there are a lot of things that are what we call normally distributed, but not everything, all right? So as you see in the notes that I gave you, the normal bell curve models many, but not all things. So for example, suppose somebody dedicated their life to charting the rainfall in a certain city. You love my imagination, the daily rainfall in Wettville. My point is, when I made this beautiful curve, somebody could study the rainfall in Wettville in a day, and let's say it ranges from 0 to 6 inches, and each one of those rainfalls would have a probability. That's what this is graphing. You'll notice that does not look like the standard normal curve. So make sure you don't just assume that when you see a variable that it's going to be what we call normally distributed. If you hear the words normally distributed, then you're able to say, okay, bell curve. So just keep that in mind. Don't always make the assumption that a variable is normally distributed. And we're pretty much going to tell you if it is. So, we're going to learn what's called the standard normal, and we're about to learn how to use a table to determine different probabilities. So in the notes, you notice that it says that if you see the variable z in a statistics discussion, we're talking about what they call the standard normal bell curve. And the standard normal, symmetrical, it has a mean of 0. So whenever you see z in a statistics discussion, you ought to go, bell curve, 0 in the middle. That's where the mean goes, all right? And then the standard deviation is 1. We talked about one standard deviation above the mean, one standard deviation below the mean. Z-scores, remember, that's how many standard deviations you fall from the mean. So for example, if you fell one standard deviation above the mean, you would be at +1. And if you fell one below, you'd be at -1. This is just like a number line across the bottom. Those are values of z, and so on. One standard deviation above, 2 standard deviations above, 2 below, things of that nature. All right? Positive values are above the mean, negative below the mean. We talked about that before. And the key thing that's going to be new for us here is the fact that areas, shaded areas under this curve, represent probabilities. See, we're not able to calculate the probability for individual values. This is a continuous situation. So unlike discrete, where we can find the individual probabilities and add them together, we have to use this visual when we deal with continuous variables. So anyway, that's the main idea. Now, here are some things that are going to come into play. So if we were to shade the area underneath this curve forever to the left and forever to the right, that would equate to the totality of all the probabilities. And we talked about the fact that if you can add up all the probabilities for a particular distribution, it will equal 100%. So keep that in mind. The shaded area, forever and ever in both directions, underneath that curve, should equal the number 1. And these are facts that we will use to piece together some of these questions moving forward. All right, if you were to shade from here to forever, and it's symmetrical, I want to point out, wouldn't that area there be half of this? This is called the upper half of the bell curve, and so if the totality of it is 1, shouldn't that shaded area from here to forever equal 0.5? Right? Yeah! All right. And likewise, if you were to shade the entire lower half of the bell curve, all the area below 0, that should also be 0.5. So these are things to keep in mind because we're going to use those facts over there to piece together some of these questions moving forward. All right, so here we go. Let's get after it. Example 1, part A. Find the probability that Z is basically between 0 and 0.84. I'm a visual person. That's the learning style I suppose you're stuck with. But here's my take on this. Whenever you see Z in a statistics question, you should go, standard normal. That's a bell curve with 0 in the middle, okay? And then you locate the values of Z that are in the question. So I would point out that the 0 here is already on the picture. Bell curve, 0 in the middle, right? All right. And then the 0.84, first of all, that's a positive number, 0.84. So it would be above the mean. Just like 0.84 is above 0 on a number line. And so that would be right there, wouldn't it? Okay. And this probability that Z is between these two numbers would be visually illustrated by this shaded area between these two numbers on that Z-axis across the bottom. So we're looking for that shaded area. Now, the problem is areas, those are easy to calculate if you're dealing with rectangles, and circles have a particular formula. But how do you find that crazy area there? You use calculus, actually. But fortunately for us, some very smart people sat down and using calculus, they created a table for us. And I will be the first to tell you that this is one of many different formats for tables. This is the table I prefer. It's the table I will provide you to reason out these questions. And so it's my preference. But anyway, whatever table you're given, whether it be here or at another school, like when you go to Princeton next year, they might give you a different table. Always look to see what type of area that table gives you. And I understand it might be difficult to see it, so I invite you to look at the notes that were uploaded where you see this table. This particular table says that if you look up a z-score, and we'll talk about how to do that in a minute, if you look up a z-score, this table will give you the area between that z-score and the middle. All right, that shaded area there. And that's exactly the first type of question we have here. So I wanted to start with one that's easy, one that's ready-made for the table. So we draw that picture, we shade the area, and then basically it's time to use the table. So table time. All right. Anyway, once you get your picture drawn, stop. Table time. Now, the nice thing about this particular example is that the area we wish to discover is ready-made. It's going to be what I'm going to call a middle sliver. It's the sliver between a z-score and the middle sliver. That's the best thing I can think of. But anyway, this z-score right here is 0.84. So what we do, see that z up there in that upper corner? I realize it's probably hard to see there, but look at the table in front of you. And you'll notice that these rows here go out to 1 decimal place. So we find the row that will get us that first decimal place, 0.8, right? And then these columns go out to 2 decimal places. And so if you think about it, the combination of 0.8 here and 0.04 across here, if we discover the intersection of that, see 0.84, so 0.84, and if you look for the intersection of that, I'm sure you can see that from as far away as you are. I'm having trouble seeing it from this close. I guess that's because I'm old. But I hope you would see that that says 0.2995. We'll practice a bunch of these, but 0.2995 is the area between here and the middle. So I'm going to draw that on my picture. And you know what? That's the answer to this question. Because this particular question, and it was designed to be an easy one, is what I would call a middle sliver. It's the area, the shaded area, between a z-score and the middle. And that's what this table provides. This is what I call, again, the middle sliver table. So anyway, that's the answer to that one. And that's part 1 of this. And we'll come back and we'll enjoy all these other pieces, and we'll talk about how they reason out in a variety of ways. So hang on, go get a cup of coffee, a sandwich or something, we'll be right back.